Today we are going to be talking about the AP Calculus Free Response question from 1999, the BC test question number 1. And I've classified this question as a type 8 question because it has to do with a parametric or vector calculus, and on this test it was a calculator active question. So we're going to start off with looking at what we have here. We're given the x position and the y position of a particle that's moving. And we're given a graph, and we're asked to answer questions about the minimum value, the position at specific times, the acceleration at specific times. So because it actually touches on speed and acceleration, I'm going to also classify this as a type 2 problem, and type 2 is particles in motion. Part A asks us to sketch the path of the particle in the xy plane and indicate the direction of motion along the path. So one approach a student might take is to go through the process of writing out a table where you're given an input of a time, and then you can plug that time into the xy coordinate given here and slowly fill out your table. Now, because this is calculator active, it's worth using our calculator to aid in this process. So the first thing we're going to do is make sure that our grapher is set to parametric mode. So we're going to be using trigonometry, so I'll make sure I'm in radian mode, and let's change from function mode to parametric. What that does is when we press y equals, we're given the xy pair, and go ahead and clear out any functions you have in there. And under the x equation, we're going to write t squared divided by 2, subtract the natural log of 1 plus t. And then we also need to include the y coordinate, which is 3 sine of t. Now, this equation is given on the boundary of 0 to pi halves. So if we go to our table setup and we start our table at 0, and we'll do delta steps of pi fourths, and we can change that to automatic. So what this does for us is gives us pi fourths, pi halves, 3 pi fourths, and finally pi halves. Sorry, not pi halves, finally pi. You could also set it to ask, and then you can type in these values, but it'll be pretty nice to do it this way. So once I go second graph, it takes me to my table, and it tells me when the particle starts moving, it is at position 0. So I'm going to put that, and that's right at t equals 0. I'll put that on the graph to note that. 0.7 seconds later, the x-coordinate is at negative 0.27, and the y-coordinate is at 2.12. And these are, of course, approximations. If you want to, you can highlight to get a more accurate decimal, but it's enough for the sketch. So negative 0.27, somewhere around here, 2.12, somewhere right here. And then we can continue at positive 0.28, comma 3, so positive 0.28, comma 3, (1.5), 2.1, 1.5, 2.1, and then at pi we get to 3.5, comma 0, 1, 2, 3.5, comma 0. And graphically, if we do a standard zoom on it, we can see that it's moving up to a high point and then coming down like that. And the direction of travel, as we see from this table, is it's heading in a direction kind of like that, finishing at t equals pi at this location. Okay. This is worth 2 points. You get your first point for having the sketch of the graph correct, and then you get your second point for having the direction of travel correct. Because remember, with parametric calculus, we get that added piece of information of direction of travel because we've introduced the parameter of time. All right, moving on to part B. Part B says, at what time does x of t attain its minimum value? So we're going to be looking for a minimum over an interval of 0 to pi, and this should spark thoughts of the candidates test to see what a absolute minimum on a closed interval is. So stage one is you have to find the derivative of the function that you're finding the minimum for. So x prime of t is t minus 1 over 1 plus t. And that tells us the derivative, and then we need to find critical values by setting the derivative equal to 0. And this is going to be some algebra that we're going to have to do. We can add the fraction to the right-hand side. We can multiply the denominator across. And finally, by writing it as a quadratic, we should be able to find the critical values. Now, in the case of this quadratic, the expression is not factorable. So solving this by hand, we'd use the quadratic formula, and we get -1 plus the square root of 5 over 2. Now, we excluded the minus the square root of 5 because that's outside of the interval 0 to pi. So there's only one critical value in there. Of course, since this is a calculator active question, we could have typed in this equation and found the 0 of it on the graphing screen. It would have required us to go back to function mode, or we can use the calculator solver to solve this. If we did that, we'd get that t is approximately 0.618. So we have the critical value that exists within the boundary of 0 to pi, and we want to know where is x of t at a minimum. So now we're going to run the candidates test. We're going to evaluate x of 0. We're going to evaluate x of pi. And finally, we'll evaluate x of that critical value, which I've stored under the value of a. Now, x of 0, we already did on the table. X of 0 is 0. And x of pi, we also did on the table. X of pi is roughly 3.5. Oops, 3.5. And now we need to evaluate x of a. And so what I'll do is go back to the calculator, and we're going to go back to the calculator. Second, sorry, not trace, and we're going to go to a t-value of -1 plus the square root of 5 divided by 2. And we get an x value of -0.29. The candidates test says the absolute maximum on a closed interval is going to have to occur at the endpoints or at a critical value. And we can see the lowest value of these three is at the critical value. So x of t is at an absolute min of -0.290 at x equals a on the interval 0 to pi. They ask at what time, so we've given the time, and what is the position. So we've given the x coordinate of the position, we just need to evaluate the y coordinate of the position. So position would be evaluated as x of a comma y of a. So once again, the x coordinate we've already evaluated, -0.290. And if we return back to our calculator, when we type that in of 0.618, gave us a y coordinate of 1.738. So there's our absolute minimum for x and the position that it occurs at. This part of the question is worth 3 points. So the first point comes from setting the derivative equal to 0. So by setting the derivative equal to 0, you're indicating you know how to find a critical value. The second point comes for actually finding that critical value. So doing the algebra to get there. And then the third point comes from identifying the position. Okay, that's 3 points for part B. And this really qualifies as the type 2 portion of this question. All right, we're going to move on to part C. And part C says, at what time is the particle on the y-axis? So if we're talking about when this particle is on the y-axis, at that location where it's on the y-axis, y of t is equaling to 0. So when the, sorry, I said that wrong, x of t is equal to 0. So when the x coordinate is 0, then the curve will be hitting the y-axis. So step 1 is to set the equation equaling to 0. And we can solve this using our calculator. It is also probably solvable by hand, but it's going to be much quicker with a calculator. And I'm going to take the graphical approach for this. So let's change our mode back to a function mode, and we'll graph this equation and find the 0 of the equation. So x squared divided by 2, subtract the natural log of 1 plus x. And we see this curve has a couple locations of 0. The first location is, of course, right at 0, where the particle started, but we're looking for that second time where the curve x of t is equaling 0. So we're going to look at that location right there. So I'll go ahead and zoom in on that location so that we get a slightly better picture of what we're trying to do. Let's calculate this 0 by second calculate, and we're finding the 0. Left of that 0 we press enter. We move to the right of that 0 and press enter, and then we put our cursor at our guess and press enter a third time, and we find the time that this curve x of t equals 0. So 1.285. So at t is approximately 1.285, which I'm going to identify as the value b, in case we need to use this. Okay, so the answer to the first question is 1.285. And now they want us to find the speed and acceleration vector. And speed, we should recall, is going to be the square root of x prime of t squared plus y prime of t squared. This tells us the speed for a particle in parametric or vector form, and they're asking what is the speed at this time. So we're going to be plugging in that value b. So for us, the speed at this time at t equals b would be the square root of x prime of b squared plus y prime of b squared. And we can turn to our calculator to evaluate that. Type this into the calculator and we wind up arriving at a speed of 1.196. So that's the second part of part C, find the speed. And now finally we need to find the acceleration vector. So actually let's back up and let's go ahead and do this on the calculator. So right after finding that 0 of 1.285, I stored it on my calculator as the letter B. And now I'm going to change my mode to parametric. Just double check that the equations are in there. Okay, and they are. And I want to take the square root of the derivative evaluated at B. So let's do math 8, take the derivative with respect to t of parametric form x prime of t evaluated at b. So this would be x prime of b. Now this value has to get squared, so we're going to close that square, and then to that we're going to do the same thing but for y prime of t. So that's parentheses, and then on the inside of our parentheses, math 8 for the derivative with respect to t, vars, y vars parametric, and this time we're taking the y coordinate, close it at b, and we're going to square that value. And if we typed everything in right, we should get that answer. Hooray! Okay, finally we want to arrive at our acceleration vector. So the acceleration is going to be the second derivative of position. We've already established that x prime of t is t minus 1 over 1 plus t, and y prime of t we have not done yet, but y prime of t is the derivative of 3 sine t, so that's 3 cosine t. And then to get our second derivative, x prime prime of t, derivative of t is 1, subtract the derivative of this would be negative 1 over 1 plus t squared, using either the chain rule with a power or using the quotient rule. We could get there. The second derivative of y with respect to t would be negative 3 sine t. So our acceleration vector would be x prime prime of t comma y prime prime of t, and then I want the acceleration specifically at time b, so x prime prime of b comma y prime prime of b gives us the acceleration vector, and we won't do that one again on the calculator, but if we typed it into a calculator, we get values of 1.191 comma negative 2.879. Okay, so this falls in the category of type 2 as well, being particles in motion. However, it is very heavy on the BC side, since we're doing particles in motion for a parametric defined particle. Right, and the point breakdown for this, 4 points. We're going to get the first point for setting x of t equaling 0. That one should come pretty easily, as well as finding when that happens. That gives us the first 2 points. Finding speed, that required the memory of this equation, and if you correctly identified the value of speed, you're going to get 1 point for that. And then finally, you get 1 point for finding the acceleration vector. So this acceleration vector is worth 1 point.